All right, everybody, welcome. So we're going to be doing a review on gravity and Coulombs Law, otherwise known to us as like electrostatics. So let's get started. So remember that Einstein said that space was like a fabric. And so we can kind of picture this out that if we were to spread this fabric out and make it kind of elastic and put some heavy masses on it, then there's going to be an indent within that fabric. And again, the same idea with space. So if we have really massive planets, again, like or stars that have a lot of mass, then they're going to make a large indent on that fabric or on space. And so things are going to be drawn to them. So keep that in mind as we go today. So Newton. So remember way back to when we were talking about Galileo, but Galileo discovered inertia. And so what is inertia? Well, inertia is the resistance to change your state of motion. And so it kind of is a property of matter. If you remember back to Bill Nye. So what inertia really is like if you have a lot of mass, then you have a lot of inertia. So a lot of resistance to change your state of motion. And so unless something is acted upon by a force, objects are going to tend to move in a constant speed in a straight line. And that even goes for our planetary objects. Okay, if they didn't or if they weren't affected by any other forces, then they're going to stay in a straight line at a constant speed. And it's not until an object undergoes a change in speed or a change in direction that a force is responsible. Think back to Newton's second law, right? F is equal to ma. If you need something to accelerate, again, changing direction or changing speed, then a force is required in order to change that motion. And so what Newton theorized was that the moon had to be falling towards the earth, and it had to be due to some type of force, again, because objects want to stay in this constant straight line motion. And so there has to be a force required in order for this planetary object, this moon, in order to keep it moving in this orbit. Not only that, but the moon itself had to have enough velocity in order to avoid hitting the Earth, right? Because if it had any less than what it has, then it would be coming towards the Earth and crashing towards the Earth. If it had any more, then it would be shooting off in a different tangent towards space. All right, so what we call this velocity is tangential velocity. So if you were to draw a circle and you were just to kind of break off from that circle and just continue in that straight line, that would be a tangent, or that would be like the speed that it would have if it wasn't affected by this force. And so Newton kind of explained this to people using this theory of Newton's cannonball theory. And so he said, okay, if I was to go to the tallest mountain and if I was to shoot a cannonball from a cannon on top of the peak of this mountain, what would happen? Well, if you didn't give it enough horizontal velocity or tangential velocity, then that object is just going to carry in a parabolic path back down to the earth. But if you give it enough velocity, if you make this thing go fast enough, what's going to happen is that it's going to continue in that motion. It's going to continue falling and falling and falling. And so we call that falling an orbit. And so that cannonball is just going to continue in that orbit, okay, around the shape of the object, in this case, the Earth. And so, therefore, again, it has to do with not only the object that is at the center, but then the object that is surrounding it. So if we go back, we look at the mass of the Earth and the mass of the moon, we can see, well, the Earth has a lot more mass than the moon, right? We can just kind of see from their sizes. And so the same idea was that Earth was not the center of the universe. And this was a crazy idea to come up with at this time, right? Because we all believed that, Earth was the center and everything was surrounding the Earth. Not true. Earth was not the center of the universe. And so again, that has to do with the mass. So there had to be another massive object within our system that was causing us to continue in this orbit. The sun in our solar system, right? So the sun has to be the major object, or in this case, the object with the highest mass, the object that is creating the biggest indent within this fabric of space. And then all planets have to be falling around that most massive object, or honestly, just falling in this orbit, right? Think of an orbit as that thing falling, or that cannonball just falling. Again, the same idea that our Earth is honestly just falling around the sun. And we have to have, again, enough horizontal velocity or tangential velocity in order for us to continue in this orbit. If we had less, we're going to be crashing towards the sun. If we had more, we're going to be shooting off into space. So this gets us into the idea of, okay, well, we're an object. We are continuing in this motion. So there has to be some type of force that is changing our acceleration, right? It's causing us to accelerate. It's causing us to change direction. We might not necessarily be changing speed, but we're definitely changing direction. So we are accelerating, right? Because constant velocity, that would be an object at a constant speed in a straight line. So what is causing us to accelerate? Well, it's gravity. So what is gravity? Well, as we've learned from our previous studies and also just from Interstellar, right, that gravity is one of the four fundamental forces of our universe. And honestly, it's just a pull between two masses. So if we have mass one, mass two, then we have to look at not only the distances between them, but the pull between them. What is the strength of this pull? Because everything is basically attracted to everything, right? I have a dog by my side right now. Well, that dog has mass. I have mass. So there's a force of attraction between those two objects. And so really, it's an incredibly weak force, right? Because this dog isn't like coming towards me and I'm not going towards the dog. And so there has to be some type of ideas where, okay, well, there has to be so much mass, there has to be so much distance in between. And honestly, what is G? What is this universal constant? Well, let's get into it. So, this is Newton's law of universal gravitation, right? That this fundamental force known as gravity is dependent upon certain things, right? Because if we're observing two masses and we're observing their distances in between, and then their interactions in between those distances and just the size of their mass, then there has to be a set guideline, right? There has to be a law between these forces. Because like I said, I have other objects around me, but there's a force of attraction, but we're not like slamming into one another, right? So every object attracts every other object. And again, it might seem counterintuitive that this is the case, but again, think that gravity is a super weak force. Like if you throw a ball up into the air, yeah, it's going to come back down. But guess what? You were able to throw it in the air. So that force isn't super strong. So, a force that is directly proportional to the mass of each object. So again, think back to what directly proportional means. That if you were to increase your mass, then that force of gravitation or the force of gravity is also going to increase directly. So double your mass, double your force. Quadruple your mass, quadruple your force, and so on. Okay, but the force is also inversely proportional to the square of the distance. So not just the distance between those objects, but the square of that distance. So again, it's going to really affect this force. The further that these objects are away from each other, the less force that that object has on the other object. Okay, so again, just to kind of recap, the law of universal gravitation, mass is directly proportional to the force of gravity, and distance is inversely proportional to the square of this force of gravity. So increase the mass, increase the force, increase the distance, decrease the force. And so what Newton didn't get was this universal gravitational constant. That didn't come along till later. And now Newton did have something in place for this. He called it a capital letter G. He just did not know what that constant or what basically the strength of gravity was. Of course, he knew it was weak. He knew that it had to be in place for the universe, but he didn't know the strength of it. So it wasn't until other experiments were invented and better theories came about where this universal gravitational constant, symbolized with the letter G, was realized. So the numerical relationship between mass, distance, and the force of gravity is this universal gravitational constant, G. It's basically the glue to all of these things, right? Because if it was not there, then we wouldn't be looking at what we're looking at, right? It just wouldn't be the data that we need. So this force of gravity is equal to G times m1 times m2 all over the distance squared. And that is the universal law of gravitation. And so basically that tells us the force of gravity. And so G is equal to 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared. Okay, so now that we've discussed the force of gravity, let's look at gravitational fields for Earth. Let's kind of focus on Earth, but know that they are everywhere, okay? So gravitational fields surround massive bodies. So again, Earth, it has a giant gravitational field. Jupiter has an even bigger gravitational field, and that's because it surrounds massive bodies. So therefore, an object with a larger mass is going to have a larger gravitational field. And so when you are an object with mass and you're in this gravitational field, then guess what? You are going to experience a force. Now, what is this force? It's the force of gravity. And I know, crazy, but honestly, it kind of makes sense. If we look at this universal gravitational constant, this force of gravity, and you are a mass, the other object is a mass, we know that G is basically the strength of gravity, then the distance between those two things is super small. Right? You're basically on the surface. Now, I understand that the center of that object, your center, it does affect G a little bit. But when we're actually just looking at the universal law of gravitation and how we get our weight, we can really just relate this back to F is equal to ma. Newton's second law. And then if we say, all right, well, we're looking at the force of gravity or our weight, well, really, these gravitational field lines represent G. They represent the acceleration due to gravity. That is the strength of our gravitational field. So 10 meters per second squared downward. And again, because we are a mass within this field, we are experiencing the force of gravity. So when we are looking at these field lines, right, we can see that as we increase our atmospheres or as we increase our distance from the center of the Earth, then the force of gravity is less on us. Okay, we have less force acting on us. So we perceive this as a difference within our weight. Okay, but we'll get that in just a second. So the field line represents a gravitational pattern. So the closer where you are to this field line, the stronger the force of gravity that you're going to feel. So any mass in the field go towards the direction of those field lines. So again, these field lines, they basically represent the acceleration due to gravity. And these field lines not only just stop at the surface of the Earth, they go all the way through the center. So when we're talking about like traveling to the core, or if we were traveling through the Earth itself, different things, different patterns are going to be present because of these field lines and the direction of which they are pointing. And so at the center of our Earth, we are going to feel weightless. That's because all of these gravitational field lines carry through and they basically cancel out one another. And so with this cancellation of G, we're going to experience no weight. The further that we get away, again, the strength of those field lines decreases. So our weight, we're going to feel like we have less weight, and that has to do with less gravitational force acting on us. All right, so now let's talk about weight and weightlessness. The force of gravity causes acceleration. And so again, think back to Newton's second law. I guess you guys really didn't guess that this would be so important, right? But honestly, the force of gravity is going to cause this acceleration. So again, we are a mass. The force of gravity, again, depends on the masses. It depends on D, and it depends on G, basically like the strength of gravity. And so the force of gravity, it causes this acceleration. And since we are in contact with the Earth, we perceive this acceleration as a pushing down on us. But in reality, it's honestly just trying to get us into the center of the Earth. It's honestly just trying to get us closer and closer and closer to the center of the Earth as it possibly can. But the Earth has a support force, right? So not only is our weight acting down, but we have the support force from the Earth acting up. And as we know, this force has to be equal in magnitude, opposite in direction, in order for us to stay here on the Earth. So this support force honestly prevents us from essentially accelerating towards the center of the Earth, where again, these masses really want us to be, right? The force of gravity is measured from the center of one mass to the center of the other mass. And so when we're looking at our gravitational fields, again, they're all pointing towards the center of the Earth. And so it wants us to accelerate towards the center of the Earth, but we have the support force that keeps us where we are. And so we experience this force as weight. And now, if you were to get further up into the atmosphere, right? If you were to increase that distance from the center of the Earth to the center of your mass, then the force of gravity is going to be less. And as we just read, the force of gravity causes this acceleration. So if the force of gravity is less on you, then the acceleration is also going to be less. And this gets us into the idea of free fall. Right? If you are matching this acceleration that is trying to get you towards the center of the Earth and you don't have any support force beneath you, then you're going to experience weightlessness. So again, if you were to like kind of take a scale skydiving and try to measure your weight, it wouldn't, because it doesn't have any support force beneath it. And so you're just matching the acceleration due to gravity. And so this kind of gets us, if we wanted to, back to Interstellar, right? And we see the central fusion module of our spaceship. And so it's continuing to spin, continuing to spin. And so what that is simulating is the acceleration due to gravity that we would feel here on Earth. Kind of cool. All right, so next thing that I want to talk about is electrostatics. So the reason that I grouped these two things together is because they have very similar ideas with Coulombs Law and the universal law of gravitation. So let's get started. So what we're going to cover is electric charges, the forces involved, and the behavior within those charges. So let's get started. What I want you to remember is this atomic model. And now we've looked at a bunch of different models. We've looked at the nuclear model that you can see right here in the GIF. We've looked at the planetary model that we can see right now. Either one is fine. It just kind of depends on like how well you visualize things. I personally like the planetary model because it helps you really see those inner and outer electrons, where the nuclear model, it's a bit more difficult. You basically kind of have to trace your finger with the electron that's orbiting around the nucleus. But that brings me to a whole nother point. But let's get started here. So remember that all things are made up of atoms, and those atoms are actually made up of subatomic particles that are known as protons, electrons, and neutrons. And now those subatomic particles have a fundamental charge. So the protons, they have a positive charge. Electrons, they have a negative charge. And neutrons, they have no charge at all. And so when we're looking at our atom, we have to look at the nucleus and on those orbiting electrons. So remember that your nucleus is made up of positive protons and neutral neutrons. And so the nucleus itself has a charge that is positive. And then the electrons that are orbiting around the outside are negative. And so, with this fundamental idea of electric charges, if you have something that is electrically charged, then there's going to be an electric field around it. And now that might be kind of weird for you to think about, but positive charges are kind of sending out this signal, and negative charges are kind of accepting that. So, when we're looking at charges and this fundamental electrical property, we know that positive charges and negative charges are going to attract because they're opposites. So there's a force of attraction between our positive charges and negative charges. And there's this mutual action between repulsion and attraction. And again, this just comes from the electrical force. And so our electric rules stem from this fundamental idea of charge. So again, like charges are going to repel. So a positive and positive, they're going to repel. A negative and negative, they're going to repel. Where a positive and a negative, they're opposites. So they're actually going to attract. And our neutrons that are neutral, so they have no charge, aren't going to do anything. They're not going to interact. And so remember that your atom is always striving for this equilibrium. All right, it's always striving to have no net charge. All right, it's striving to not have any charge at all. It's striving to be neutral. It wants an equal number of protons to an equal number of electrons. So again, protons positive, electrons negative, no charge. But when your atom does have a charge, we call that an ion. And so it can either be a positive ion if it's lost one or more electrons, or it can be a negative ion if it's gained one or more electrons. All right, so again, if it loses that negative charge, then it's going to be more positive. If it's gained more negative charge, then it's going to be more negative. And so the electrons are the only thing that is being transferred within your atom. And so the innermost electrons are strongly attached to the nucleus. Why? Well, the electron is a negative charge. Your nucleus is positive. So the closer that you get to that more positive charge, the stronger the force of attraction between them. And so if you were to continue to separate that distance, like bringing that electron out on a further shell, well, then that force of attraction is going to be less. So it's those outermost electrons, which we call the freely flowing electrons, that are going to be the ones that are going to get transferred. And so honestly, just depending on the layout of your electrons within the atom, we're going to see that some materials are better at transferring these electrons than others. And so when we're looking at this transfer of electrons, what we really want to focus on, again, like I said, is the material. And so we have insulators and we have conductors, right? So our conductors are really good at spreading this electric charge through the material because they allow freely flowing electrons. Where our insulators, they kind of just take in this charge, but they don't allow it to spread. They just kind of keep it there. And so that's why when you have like a break in your insulator, it gets really, really hot and it has the potential to kind of cause a fire because again, it's not allowing that spread of charge to go throughout the material. So it's honestly just going to take this electrical charge and turn it into thermal energy, and that's going to create heat. And then with more heat that's added, bad things happen again. And so when we're looking again at the conservation of charge, electrons cannot be created nor destroyed. They can only be transferred. Again, this is similar to our ideas of energy, right? We can't create nor destroy energy. We can only transfer energy. And so when we are looking at how we can transfer these charges, again, what we're really focusing on is the movement of our electric charge. There is 3 ways in which we can do that. We can charge things by friction. We can charge things by induction. We can charge things by contact. So a good example of charging things by friction, if you were to take a balloon and start rubbing it against your hair really, really fast, you're going to move electrons from your hair to the balloon. And so what you're going to have happen is your hair is going to start to stand up. Again, so you have actually charged your head by induction. Sorry, by friction. And so we can also charge things by contact. And so if we were to have like a metal orb and we were to charge that object, then the electrons are going to flow, again, causing your hair to stand up. Where charging by induction, that charged rod that is more negative in this picture, but it can also be more positive, is not going to touch that other object. Okay, that other object that is neutrally charged, it's not going to touch that object. It's just going to be around it, just in the vicinity of that object. And so what's going to happen is, again, those electrons are going to move. Because this rod is more negatively charged, it has more electrons than what it requires to be neutral. That rod's electrons are going to transfer from the rod itself to the object that is neutral. Again, it's because it's trying to get rid of those electrons. Okay, um, so that brings us to Coulombs law. So when we're trying to look at this electric force, right, this force of attraction or this force of repulsion, it kind of is similar to our force of gravity. If we were to compare them, well, like it would be directly based off the magnitudes of the charges instead of the masses that it was before. So what this means is that the force of, the electrical force is going to directly increase if you increase your charge values. It's going to directly decrease if you decrease your charge values. If you were to increase the separation between your charges, there's going to be a decrease in that electrical force. If you were to if you were to decrease that distance, then there's going to be an increase in your electrical force. So again, inversely proportional there, and it's also inversely proportional to the square. So another important thing about Coulomb's law, we can have positive and negative charges, right? So this electrical force is not only a force of attraction, but it's also a force of repulsion, or it's a force that can repel. And again, that's different from our force of gravity. This force of gravity is only a force of attraction. And so when we're comparing them, again, Q1, Q2, that would be charge 1 and charge 2. Now that charge, it can be negative or positive. So we can look at the force between a positive, a negative, or a positive and negative. D is the distance between those particles. And now we have a new constant. This constant is called K, and it's the electrical proportionality constant. So again, it's just this constant that binds together your charges and your distance so that we can get this force of electrostatics, or this electrical force. Okay. And so again, just to kind of overarch these ideas, gravity only attracts. The electrical force may attract or repel. The electrical force is a stronger force compared to your force of gravity. All right, so remember that the force of gravity is a very weak force. Your electrical force is a strong force. And the reason that we know is just the constants. The constant of K is 9 times 10 to the 9th Newton meter squared over Coulomb squared, where G is 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared. And so, again, just really different magnitudes. K is a very large magnitude, G is a very small magnitude. And that sums things up. If you have any questions, please feel free to ask, and you can get started on those mini activities or on your classwork.